So, how many of you are in pre-calc trig right now? Okay, and then people who are in calculus have taken pre-calc trig. So, the periodic motion, you really need trig to understand periodic motion well, because if you think about, what do you think if I were to graph here for the pendulum, if I were to graph the displacement, let's say we're going to graph how far it is to the side of a vertical line stretch that extends right beneath my hand. So it's moving to the right by a certain amount, now to the left by a certain amount, etc. Right? So if we were going to call that, let's call that x. So that's going to be our x-axis, which is displacement, and that's time. What do you think the curve would look like if I were just to graph? Once again, I'll see it one more time. If I were to graph the horizontal displacement as a function of time, where's it moving the fastest? Right in the middle. When it gets up to the limits of its motion, it moves quite a bit slower. Right, it comes to a stop. So what do you think?
Wait, the x is what?
The x is the displacement from vertical to the sides.
So it's going to be just like this.
Yeah, just like a sine or a cosine wave. It doesn't that make sense? If you think about it, if I move my hand at constant speed across the board, we said it was going the fastest down here, right? So it looks something like this. If I move my hand sideways across the board, it's just going up and down. It should be symmetric about that, but it's just a sine curve, isn't it? Right? So those of you who, well, I don't want to get, you haven't had trig, not very many of you have actually had trig, but we would say that for a continuous wave like this, right, which you see a lot in physics. Okay, so if we want to talk about one wavelength, what am I talking about? Okay, yeah, it's from one place back to the identical place in the next wave, right? So for example, we could start here and we could go down until it's back up to the top again. Or if we wanted to, we could start like right here. And then we'd have to go down until it's back to that point again, moving up on the x-axis. No matter which one you do, the wavelength is the same, right? If the wave is being measured as a function of time, then the length of that wave, the length it takes to go through one complete oscillation in this case, right? So think about what the plumb bob is doing here. It's swinging out and back to there. So that's going to be what we call a period, right? The time it takes to go through one complete cycle is called a period. So it turns out that period, our physics, the symbol we assign to period is T. What do you suppose the L is, the script L up there?
The length.
Yeah, the length of the pendulum. So the length from where it's suspended to where the mass is. Okay. And once again, this is an idealized case. It's a simple pendulum, meaning that if this is let's say that's the fulcrum, and this is L, then we're assuming that the mass at the bottom is a point mass. If it's not a point mass, this equation doesn't work perfectly, but it's a good example, right? See what I'm saying? You could, like for example, if you were to take what if you were to take what's called a physical pendulum? Which is like this. Okay, if I were to swing this back and forth, what you're going to find is that the equation is slightly different than what we had for the other one. Okay?
Because its mass is equal throughout.
Because the mass is distributed throughout. But here's the thing. If you just think, oh, well, the center of mass is in the middle, right? So we could just treat this like a simple pendulum with the mass right there, you'd be wrong. It turns out that the mass that's further away from the fulcrum has a greater impact on the swing. And so that's why even if you had something like we had there, maybe instead of this being a point, it was just a small lead sphere. Even that's going to be very close, but even that, because the mass is not at one point, the particles of lead that are a little bit closer to the fulcrum are going to have a little less impact on the swing than the particles at the bottom. It's very, very small, but this is kind of an idealized model that we use to approximate things like we always do in physics pretty much, right? All the stuff we do, they're just models that work pretty well. None of the stuff you're learning this year, I wouldn't say none of it, but almost none of it is going to be exactly correct. It's just a lot of it is really close to correct for our scale of the universe, right? They're just good, easy models to use, but they could be improved on if you want to be extremely precise, if that makes sense. Okay, so then tell me then, based on this, what does G stand for? No, what's G stand for?
Gravity.
I heard it. So it's the acceleration of gravity wherever the pendulum is sitting, right? So on Earth, that would be 9.8, right? But on a different planet, it would be something different. So the pendulum would behave differently on the moon than it did on Earth, for example, right? Give me a relationship here. As the length, if L is in the top of this fraction and period t is on the other side, if we hold the gravitational constant equal, so assume that this is staying in the same place, does it make sense now why if L increases, t increases, right? Think of the behavior as of a fraction. And sure, the fraction's under a square root, right? But big deal. It's still, that means we're going to take the fraction's value and then square root it. But the square root of a big number, the square root of a number bigger than 1 is still bigger than 1, right? And the square root of a number less than 1 is still less than 1. If I increase the size of the argument of the square root, so if I increase the size of the quantity inside the radical, doesn't the square root's value still go up? Would you agree? And if I decrease the size of the value inside the radical, then the square root's value also goes down, right? Okay? So then it makes sense because a fraction goes as its numerator goes, right? If the numerator increases, the fraction increases. If the numerator decreases, the fraction decreases. So that's a pretty obvious correlation we can make. As L increases, the period t increases, and we saw that, right? What about the gravitational strength, the acceleration of gravity? What's the correlation going to be there? If we did this on the moon, what would we expect to happen?
So smaller gravity is bigger t.
Okay, smaller gravity means bigger t because look where the gravity, or the acceleration of gravity sits in that fraction. It sits in the denominator, and has an inverse relation to the size of the fraction, right? The bigger the denominator gets, the smaller the fraction gets, right? Like 1/100th is less than 1/10, right? And vice versa. So you'd expect that as the gravitational strength, the gravitational acceleration goes down, that the period of the pendulum is going to go up. It's going to take longer to swing back and forth. Does that make sense? Okay. And something else you can do in physics is you can, a lot of times, I really like this. In fact, I'm even going to write it up here. Use the principle of exaggeration. Did I spell exaggeration right?
Sure.
I think so. 1 G or 2? 2. It must be 2, right? Or I don't know.
Yeah, looks alright.
Yeah, I don't know. Looks good enough. So anyway, the principle of exaggeration, this is a really valuable thing to do. A lot of times in physics, if you've got a relationship, you could say, okay, well, what if we were to exaggerate one of these quantities out to an absurd level? You know, what would happen? Does the behavior of the equation match what you'd expect? Like, what could you do up here with this one, for example? How could you use the principle of exaggeration to kind of verify for yourself that as the acceleration of gravity goes down, the period goes up?
Throw in like 1.
You could. You could throw in a specific value like 1, but I'm even thinking exaggerating it more than that. Yeah. What if the gravitational acceleration approached 0? What would you expect to happen there?
Just go in a circle.
Yeah, then the pendulum at some point, when it actually sneaks down to 0, the pendulum's not going to go anywhere, is it? The length of a period would be infinite, right? So if you went down close to 0, wouldn't you expect that pendulum to just about not do anything, right? You see what I'm saying?
Like,
Right.
are you talking about like if we pushed it or if we just brought it up and then dropped it?
Well, I'm saying if you just brought it up and dropped it. right? Like if you just let it go. Like just imagine you were starting at the Earth's surface and you were using a magical elevator that took you up from the surface of the Earth as long as you wanted to. Every once in a while, we're going to stop and do this experiment where we drop the pendulum and see what happens. At some point, you're going to be far enough away that you're essentially in interstellar space, and when you drop it, nothing happens, right? Does it make sense though that that's not going to be some immediate threshold where 1 minute it's moving and the next you move a meter further and it just stops? Right? That's not going to happen. It's going to gradually progress to a point where it doesn't swing at all. So do you see my point with the principle of exaggeration, how you could apply that? You could say, okay, well, if that's what must happen way up there, then between here and there, we must gradually morph from swinging at a certain period, with a certain period to infinite up there. The further I get away, meaning the smaller g gets, the bigger the period must get. I don't think I articulated that very well, but you kind of get what I'm saying about the principle of exaggeration. If you take it to the extreme, a lot of times you can test your hypothesis and see if it holds up in the extreme values, and you can a lot of times either verify it or disprove it that way. Okay? Questions? Let's look at a quick problem involving that. And you just tell me these are really simple. Okay, let's see.
First breath in 5 years.
Okay, so how about this? How would I do that?
Well, you have the period length, you just need to find out.
Okay.
So,
Yeah. Okay, good. So we're really all we got to do is start with our model, which is the equation, and then this is what we're given. Find out what we're solving for, and isolate that variable, right? So we'll go back to. So let's go back to here. I'll get rid of all this garbage. Okay, so there's our model. What are we solving for? L. Okay, so then what are the steps we go through here? Let's just look at the algebra of this real quick. So if we're solving for L, we're going to isolate, we're going to just do a little quick algebra review here. We're going to isolate a variable. We can always isolate a variable by reversing order of operations, right? So we start with t equals 2 pi times the square root of L over G. And here's our order of operations tree. What goes P, what?
M, E, like
What?
M,
D together, right? They're equal. And yes, right? Okay, so we're going to work our way up. So we want to isolate the L. So what's the first thing I would do? Divide by 2 pi, right? So what does this mean? We're going to undo any loose addition or subtraction. I don't mean to insult you by going through this stuff, but I really think every once in a while it's not bad to just kind of remind yourself what you're really doing when you do algebra. Loose addition or subtraction means addition or subtraction outside of parentheses. None of that. Next step is undo multiplication or division. Well, yeah, we're multiplying the radical by 2 pi, and so we've got to divide both sides by 2 pi, right? Okay, so that leaves us at the point t equals the square root of L over G.
T over 2 times 2 pi.
Oh, over 2 pi, whoops. Okay, now what?
Square.
Okay, good.
Plus or minus. Plus or minus.
So we've got to deal with any exponents. Now, this is a weird one. Why does a radical count as an exponent? Because it does. Exponents.
It's to the 1/2 power.
Okay. Because a square root is the same as a 1/2 power, right? So we could say this, the square root of a, or a is just some number, could be written as a to the 1/2 power. Okay, they're identical. So that means that a square root, even though we write it as a radical, it really is a power, and so we've got to undo that exponent. Well, how do I undo square rooting? Square. Okay, I'm going to square both sides. Okay, if I square both sides, I don't include a plus or minus, but I do have to be careful about something. If I solve an equation by squaring both sides, so I'm solving a radical equation like this, it means that there's the possibility that I introduced an extraneous solution. Remember talking about this in Algebra 2? Okay, so that means that whenever you solve by squaring or taking any side, by taking both sides to a power, you've got to check your solutions back in the original equation to see if they actually work. Because they might not. It's possible that they won't, because they could be false solutions that you created by squaring both sides. We call them extraneous solutions. Okay, so what's that do algebraically then? It undoes the radical. I'm going to flip this around so the L's on the left side. So we get L over G equals the quantity T over 2 pi squared. Last step? Yeah, and really, where do the parentheses come in?
No, they're right there.
They're implied. Why are they implied in this case?
Because LG has parentheses around it.
Okay, because
you're squaring.
Oh, that corresponds.
yeah, whenever you take a function of something, then that something is considered to be a quantity, right? So if we're taking the square root of some stuff, there are implied parentheses around that stuff that's in the square root, right? Just like if a square root is equivalent to a power, what if I had, for example, what if I had the square root of a plus b? Then that would have to be the quantity a plus b to the 1/2, correct? So I need those parentheses, right? Even if we don't write them, they're there. So finally we get up to the parentheses layer, which is the stuff that was inside the square root, and all I have to do there is multiply both sides by g. Okay, so then we got it. So our answer looks like L equals G times the quantity T over 2 pi squared, right? And we'll just plug in our values. Okay, so let's throw that in a calculator. Oh, what's that doing?
Forward.
Yeah.
Do it again.
Okay, so what do we got then? Let's plug and chug on our calculator, put everything in at once. Okay, so we've got 9.8 times the quantity. What was the period? Remember? 0.765. Okay. Uh-oh. 0.765. Divided by 2 pi. So what do I need to, if I'm not going to use the fraction template, what do I need to do now? I need to put the 2 pi in parentheses because they're all in the denominator, so there are implied parentheses there as well. So 2 pi, and then I close both sets of parentheses, and we get the answer 1.19. Okay. Oh, I didn't square it though, did I? You're right. So I got to go back up here. Let me go grab this. And I forgot to, come on now. I forgot to put it squared there, right? Square everything in the parentheses. So now we get 0.15. How many sig figs do we get to keep? I think we get to keep 3, don't we? There's only one measurement. Yeah. Okay, I didn't. I squared a number smaller than 1, which made it smaller. Think about if you square 1/2, you get 1/4.
Oh, yeah, you don't.
I didn't square the 9.8 part. I squared the other part.
Thought the parentheses went all the way out.
Oh.
So where could we go to verify that that worked? I mean, it's going to work, but I could just go back to the original, right, and plug that in and see. Okay. But here's how you could kind of justify this. Okay, and this is going to sound hokey again, but I want you to just kind of hear this reasoning. So, would you agree? How many solutions did we get? 1. Okay, is there a solution to this? There must be, right? I mean, there's no way that there's not. Agreed? That if we have a pendulum that has that period, some pendulum in the universe with a gravitational field of 9.8 would give us that period, right? There's some length that would work, agreed? So if we only got one solution, what does that mean?
That's the only one.
It's the right solution, right? You see that reasoning? That's true. That works. Okay, so we can plug it in and see. Oh, that'd be embarrassing if it doesn't, huh? 0.145. Oh, I had to put units in. Oh no, meter. No, wait, meters? Yeah.
Yeah.
Right. Oh, phew. Okay. Okay, I think that's. You got it. Yep, we can go work. We're good.
We got like